Trillions of years from now, the last remnants of a once great civilization stand like fading spires in the dark, monuments to an age of brilliance long extinguished. In their prime, they reshaped entire star systems, dismantling planets and harvesting asteroids to forge a vast interstellar empire. But now, in the twilight of existence, all of it is gone. Around them, the universe itself is dying. The final stars flicker and fade, and across uncountable millennia, the heavens dim into an endless night. The cosmos, ancient and exhausted, sinks into ruin and decay. And so, in the deepening dark, they wait for the end. Long before the last light began to fail, they understood the truth. The universe was on an irreversible path toward decline. Determined to endure for as long as time would allow, that they undertook their final and greatest feat of engineering. Around a solitary, wandering black hole, they built a new home from the shattered remains of worlds. They forged a colossal shell encasing the abyss itself. Within that fragile sphere, strained to its limits by the immense gravity of their unlikely savior, they clung to existence. The faint glow of dying stars washed over their last sanctuary, while the swirling black hole at its heart was harnessed to power their survival. Yet it offered them more than energy. It gave them time. No one remembers the name of the scientist who first uncovered the true nature of time, but these cosmic engineers understood. Time does not flow equally throughout the universe. Here, deep within the crushing grip of gravity, time slowed. While ages swept by in the wider cosmos, only moments passed inside their immense sphere. They watched the distant future unfold in accelerated silence, knowing they had not escaped extinction, only postponed it. Eventually, even they would surrender to the dark. This story, of course, is speculation, but it is rooted in an idea that transformed our understanding of reality. More than a century ago, Einstein's theory of relativity shattered our comfortable notions of space and time. What once seemed absolute, ordinary, unquestioned, was revealed to be far stranger and more profound. What is space made of? Does time truly flow, or is it something else entirely? And if we continue to pursue their deepest nature, will we arrive at a sudden, illuminating clarity, or uncover mysteries even darker than the void itself? And the deeper we look into space and time, the more elusive they become. There is a story from 1915. Einstein invited a few colleagues to lunch. They gladly accepted. He cleared a stack of papers from his desk, opened 4 cans of beans with a can opener, warmed them, placed a spoon in each can, and that was lunch. Albert Einstein was a busy man, so absorbed in reshaping our understanding of reality that he often forgot to eat. More than a century later, our lives are no less frantic. If anything, they are faster, louder, more crowded with distraction. Yet while the pace of daily life accelerates, the questions Einstein grappled with remain as vast and unsettling as ever. What is time? What is space? And what kind of universe have we truly been living in all along? In our imagined future, a civilization bends itself around a black hole to stretch out its remaining moments. They can curve reality, but they cannot escape it. That is the quiet power of relativity. Gravity does not merely pull on matter, it reshapes the very stage on which existence unfolds. It warps the fabric of space and slows the flow of time. The cosmos is not a rigid backdrop. It is supple, dynamic, responsive. And behind all of this may lie an idea so simple, so inevitable, that one day, whether in a decade century, or a millennium, we may look back and ask, how could it have been otherwise? How did we not see it sooner? So what is space? At first, the question feels almost meaningless. As children, we learn to navigate the world through directions, up and down, left and right, forward and back. We call this arrangement three-dimensional space, and we move through it without hesitation. It feels obvious, familiar, solid beneath our feet. But what is it truly? What is this cosmic foundation upon which galaxies spin and civilizations rise and fall? The question haunted the earliest philosophers. In the 4th century BCE, Plato described space as a kind of receptacle, a cradle of becoming, an invisible medium in which all things appear, yet which possesses no qualities of its own. His student Aristotle rejected the notion of empty void altogether. To him, a true vacuum was impossible. Nature, he believed, abhorred emptiness. For more than 2,000 years, these ideas lingered in debate. Only in the 17th century, as modern science began to take shape, did space become something that could be described in mathematical language. The universe was no longer explained through myth or metaphor, but through laws, precise, elegant formulations that seemed to govern motion, a force and matter itself. And yet, even as those laws brought clarity, they also deepened the mystery. Because once we began to measure space, to calculate it, to formalize it, we were forced to confront a more unsettling possibility. Space is not just where things happen. It may be something far stranger. Of course, Isaac Newton would later dominate this revolution in thought. But before Newton, we must return to a ship at sea. In 1632, an aging Galileo Galilei published his great work, Dialogue Concerning the Two Chief World Systems. He was already in his 60s and had repeatedly drawn the suspicion of the Roman Inquisition for daring to claim that Earth moves around the sun. So he wrapped his radical insights in conversation and allegory, quietly embedding his most profound ideas about motion, space, and the structure of the cosmos within the pages of a book. At one point, he asks us to imagine a sailor inside the windowless cabin of a ship. On the table rest plates and cutlery, a bowl with a goldfish gliding lazily through water. Birds flutter in cages, flies and butterflies drift through the air. When the ship is anchored in harbor, everything is serene. The goldfish swims peacefully. The dishes remain still. The insects hover gently. Now imagine the sea grows rough. The ship pitches and rolls. Plates slide from the table. Water sloshes from the bowl. The sailor feels the violent motion unmistakably. But then the storm passes. The sails fill with steady wind. The ship accelerates smoothly until it glides at a constant speed across calm water. Inside the cabin, tranquility returns. The goldfish swims as before. A dropped object falls straight to the floor. The sailor, seated comfortably, feels no motion at all. And here, Galileo realized something extraordinary. Without windows to the outside world, no experiment inside the cabin could reveal whether the ship was at rest or moving uniformly. There is no absolute state of rest. Constant motion feels indistinguishable from stillness. With that insight, the first principle of relativity was born. Motion is not absolute. It is always relative to something else. Galileo's sailor drifts gently across the sea near Earth's equator, unaware that he is spinning at 1,600 kilometers per hour with the planet, orbiting the sun at 67,000 kilometers per hour, carried by the sun around the Milky Way. at 720,000 kilometers per hour, while the galaxy itself hurtles toward Andromeda at 403,000 kilometers per hour. And yet he feels nothing. No grand cosmic voyage, no roaring speed, only stillness. For this and other heresies, Galileo was condemned. His book was banned and would remain on the Church's index of prohibited books until 1835. But the ideas could not be silenced. They had already set the stage. A few decades later, two of Europe's greatest minds would clash over the nature of space itself. Isaac Newton and Gottfried Wilhelm Leibniz. Newton, born in 1642, the year Galileo died, needs little introduction. He reshaped mathematics, optics, and mechanics, becoming one of the most influential thinkers in history. Leibniz, born 4 years later in what is now Germany, was equally brilliant, a philosopher and mathematician who asked questions so deep they still echo today. Why is there something rather than nothing? Their rivalry began over the invention of calculus. Leibniz published first. Newton accused him of theft. As president of the Royal Society, Newton even oversaw the committee that judged the dispute, unsurprisingly ruling in his own favor. The bitterness spilled into a deeper disagreement. What is space? Newton argued that space is absolute, a rigid, universal stage upon which motion unfolds. Even in an empty universe devoid of matter, space and time would still exist, unchanged and immovable. To illustrate, he proposed a simple thought experiment: a bucket of water. When the bucket is still, the water's surface is flat. Spin the bucket, and eventually the water begins to rotate too, its surface curving upward along the edges. Newton asked, relative to what is the water rotating? If everything nearby were removed, if the universe were empty, would the surface still curve? He answered yes. The rotation, he claimed, was relative to absolute space itself. Leibniz disagreed. In an empty universe, he argued, space would be meaningless. Space is nothing more than the relationships between objects. Remove the objects, and space disappears with them. The same, he believed, was true of time. Without events, without change, time has no role and no existence. Leibniz died in 1716 with the debate unresolved, but history sided with Newton. For nearly 2 centuries, science embraced the idea of absolute space, unchanging, independent, always the same, and absolute time, flowing uniformly on its own, unaffected by anything in the universe. Galileo had dismantled absolute rest in space, but time remained untouched. According to Newton's vision, clocks across the cosmos ticked in perfect synchrony. 1 second on Earth was identical to 1 second anywhere else. Time was a universal metronome, carrying the universe forward with steady precision. But is that truly so? Is time flexible, or is it an unyielding rhythm? Does it possess properties of its own, or is it merely the measure of events unfolding within it? To approach these questions, we must return to our distant, dying civilization orbiting its ancient black hole. They sit and wait, because waiting is all they can do. As stars fade and raw energy becomes the most precious resource in existence, they slow their own lives to conserve it. Every aspect of their world is tuned toward survival. As their weary eyes watch the sky darken, they understand something profound. Time is their ultimate enemy. You may see a teacup fall from a table and shatter across the floor, but you will never see the shards gather themselves and leap back into the shape of a cup. Time has direction, a past, a future. Unlike space, we cannot wander freely within it. Ancient thinkers wrestled with this mystery. Aristotle described time as the measure between before and after. Hindu philosophers envisioned vast cosmic cycles, creation and destruction unfolding across billions of years. Yet the origin of time itself remained elusive. Like space, time feels obvious, ever present, and yet it is fundamentally different. We cannot step sideways into yesterday or tomorrow. It carries an arrow pointing relentlessly forward. Scientists may treat time pragmatically, combine a ruler and a clock, conduct an experiment, record the results. But practicality does not dissolve the deeper question. What is time, really? And why does it flow the way it does? So if we truly want to understand time, we must begin not with clocks, but with horses and steam engines. At the dawn of the Industrial Revolution, humanity faced a practical dilemma. For centuries, civilization had been powered by muscle, horses, oxen, livestock. Their economics were simple. A certain amount of hay produced a certain amount of labor. Feed the animal well, and it worked well. But what about machines? How much work could you extract from a pile of coal? Could a steam engine outperform a horse? And at what cost? This was not merely a scientific curiosity. It was an economic necessity. Mines, factories, railways, all depended on the answer. From this question, thermodynamics was born. Our early steam engines were astonishingly inefficient. Many converted only about 3% of the coal's energy into useful work. The rest vanished. Heat escaped into the air. Metal parts screeched and glowed as friction devoured precious energy. Loss seemed unavoidable. And that was the revelation. Perfect efficiency is an illusion. As energy flows through any system, it degrades. Concentrated energy, like the chemical potential locked inside coal, inevitably spreads out. Some of it becomes unavailable for work. Some of it dissipates into the environment. The universe keeps the books, and it always demands a loss. To quantify this drift toward disorder, physicists introduced a new measure: entropy. Entropy is not merely chaos, but probability. It describes how many microscopic arrangements correspond to what we see macroscopically. And probability has a direction. Physicist George Gamow once offered a haunting example. The air in the room around you is evenly distributed, wall to wall, floor to ceiling. You never fear that in the next moment, every molecule might spontaneously gather in one corner, leaving you gasping in vacuum. Such an event is not forbidden by the laws of physics. It is simply unimaginably improbable. The waiting time for such a fluctuation exceeds the age of the universe by trillions upon trillions of times. Disorder is overwhelmingly more likely than order. Thus, the laws of thermodynamics revealed something profound. As the universe evolves, entropy increases, not just in engines, not just in factories, but in planets, stars, galaxies. Every structure moves statistically from order toward greater disorder. In 1862, Lord Kelvin followed this logic to its grim conclusion. If the universe is finite and governed by these laws, then although energy cannot be destroyed, its usefulness steadily declines. Eventually, all energy differences will be exhausted. No gradients, no work, no structure, a final equilibrium, a heat death. Stars will burn out one by one, their nuclear fuel spent, leaving behind a cosmos trillions of years old, dark, cold, and thinly scattered with embers. The same fate that haunted our imagined civilization orbiting its ancient black hole. Among those who wrestled most deeply with entropy was James Clerk Maxwell. He understood that if you mix hot gas and cold gas, you get warm gas, and it stays mixed. Heat does not spontaneously unmix itself. But Maxwell imagined a tiny demon. This creature could observe every individual atom. It could open and close a microscopic door between two chambers, allowing only fast-moving atoms to pass one way and slow-moving atoms the other. Since temperature reflects average molecular speed, the demon could separate warm gas into hot and cold again, apparently reversing entropy. It was only a thought experiment, yet for more than 150 years, physicists debated its meaning. Some argued the demon must expend energy to sort the atoms, ensuring total entropy still rises. Others realized something subtler. The key is information. The demon must measure, record, and process data about each atom's speed. And information, it turns out, is physical. Over the past century, the link between energy, entropy, and information has grown stronger. Anyone who has used a computer knows that computation produces heat. But the deeper insight is this: it is not calculation itself that necessarily generates heat. It is erasure. Consider a simple example. If I tell you that 3 plus 2 equals 5, that is straightforward. But if I tell you only that the answer is 5 and ask what two numbers produced it, you cannot know. Information about the inputs has been lost. Inside a computer, logic gates combine electrical signals to produce outputs. In doing so, they often discard the original inputs. That act of forgetting is irreversible, and irreversibility carries a thermodynamic cost. In 1961, Rolf Landauer showed that erasing just one bit of information releases a tiny but unavoidable amount of energy, now called the Landauer limit. At room temperature, it is minuscule, a fraction of an electron volt. Yet it is real, confirmed experimentally in 2012. All modern computer chips still operate far above this limit, but as technology advances, they edge ever closer. Every forgotten bit slightly increases the entropy of the universe. Irreversibility, whether in steam engines or silicon chips, drives entropy forward. And entropy, in turn, defines the arrow of time. We never see the shattered teacup reassemble itself because that would require an astronomically improbable reversal of entropy. Yesterday feels different from tomorrow because information is continuously lost, smeared into microscopic degrees of freedom we cannot track. So we are led to a troubling possibility. Is the flow of time inseparable from forgetting? Does the distinction between past and future emerge because information about the past disperses irreversibly into the environment? And if that is true, or then what happens in the far future when entropy reaches its maximum, when no usable energy gradients remain, when nothing meaningful can change? In that final equilibrium on the brink of cosmic heat death, does time still have meaning at all? And so we arrive at a turning point. The foundations of modern space and time have carried us far, but not far enough. Newton's absolutes fractured. Thermodynamics gave time an arrow. Yet another revolution was waiting in the wings, one that would bend reality itself and guide us inevitably back to the final days of our lonely black hole world. Inside their vast shell, wrapped around the abyss, many among that fading civilization had already surrendered. With energy dwindling, some chose chemical sleep over cosmic patience. But a few restless minds remained awake. Surrounded by the accumulated knowledge of near-eternal libraries, they returned to a central story, the story of light. They had long known that light travels extraordinarily fast. They had used it to measure the breadth of their empire. They knew it was a limit no engine, no ambition, no technology could ever surpass. And they knew that understanding this limit was the first step toward understanding the universe itself. Step outside on a clear summer night and look nearly straight above you. There shines Vega, the brightest star in the northern sky, 26 light years away, close by cosmic standards, but impossibly distant for beings as brief as we are. No traveler could journey beyond Vega and return home within a single lifetime. Light itself takes 26 years to bridge that gap. For centuries, its scientists wondered whether light's speed was infinite. Early experiments showed it far outpaced sound, but was there any limit at all? In 1676, Danish astronomer Ole Rømer found the answer by observing the moons of Jupiter, particularly Io. He noticed something strange. Their eclipses did not occur precisely when predicted. As Earth moved farther from Jupiter in its orbit, the eclipses seemed delayed. As Earth moved closer, they occurred earlier. The explanation was subtle but profound. Light itself required time to travel the extra distance. From Rømer's data, Christian Huygens estimated the speed exceeding 200,000 kilometers per second, astonishingly close to the modern value of nearly 300,000 kilometers per second. Light was not instantaneous. It was finite. 2 centuries later, James Clerk Maxwell deepened the mystery. He unified electricity and magnetism into a single framework, electromagnetism, and discovered that light is nothing more than a self-propagating electromagnetic wave. Its tremendous speed emerged naturally from his equations, but those equations left a haunting question unanswered. Relative to what is that speed measured? If light is a wave, perhaps it travels through some invisible medium, an all-pervading ether filling the cosmos. Yet such a medium would define a universal state of rest, reviving the very absolute frame Galileo had dismantled. Physicists searched desperately for this ether. Experiments probed for signs of motion through it. None were found. Then a young patent clerk named Albert Einstein asked a radical question. What if the problem is not with light, but with our assumptions? Why should electromagnetism violate Galileo's principle? Why should experiments with magnets and currents reveal absolute motion? In 1905, Einstein made a bold declaration. They cannot. From this came special relativity. Galileo's ship returns, but transformed. Whether the vessel rests in harbor or glides smoothly across calm seas, every experiment inside yields the same result. And this applies not only to thrown balls or falling plates, but to measurements of light itself. The speed of light in vacuum is constant for every observer. This shattered Newton's mechanics. In Newton's universe, velocities simply add. Run forward on a moving ship and your speed increases relative to the shore, but light refuses to obey. No matter how fast you chase it, 50 knots, 50,000 knots, you will measure the same speed. If that is true, then something else must give. The only remaining freedom lies in space and time. To preserve light's constancy, each observer must possess their own measurements of length and duration. Space contracts, time dilates. What was once absolute becomes relative. Light is the invariant. Space and time are not. And just as Maxwell united electricity and magnetism, another union was imminent. In 1908, Hermann Minkowski, Einstein's former professor, stepped forward with a revolutionary insight. Space and time, he argued, should not be treated as separate entities awkwardly mixed by equations. They are already one thing. From now on, he declared, space by itself and time by itself shall fade into mere shadows, and only a union of the two shall preserve an independent reality. Thus was born space-time, are 3 dimensions of space and 1 of time fused into a 4-dimensional geometric structure, Minkowski space-time. Transformations between observers became rotations within this unified geometry. Reality itself acquired a new architecture. Minkowski died tragically in 1909 before his vision was fully embraced. But even this was not enough for Einstein. Special relativity revolutionized motion, but gravity remained untouched. Newton's gravitational force depended on distances between masses. Yet special relativity had already undermined any universal agreement about distance. Einstein returned to his desk and wrestled with gravity for nearly a decade. In 1915, he emerged with general relativity. He took Minkowski's space-time and made it dynamic. Mass and energy do not merely reside within space-time. They curve it, stretch it, warp it. Gravity is no longer a force pulling across empty space. It is geometry. Objects follow the curved pathways carved into space-time itself. Newton's rigid stage was gone. Space and time were not only relative, they were flexible. The consequences were staggering. Special relativity had shown that moving clocks tick at different rates. General relativity went further. Clocks tick differently depending on where they are. Near massive bodies, time itself slows. The deeper you descend into gravity's well, the slower your clock runs. Which brings us back, inevitably, to our dying civilization orbiting a black hole. They were not merely harvesting energy. They were living inside curved time. The following year, in 1916, Carl Schwarzschild found an exact solution to Einstein's field equations for a spherical mass. Buried within his mathematics was something extraordinary. A mass compressed to a single point, wrapped in a boundary from which nothing, not even light, could escape. It would not be called a black hole for another 50 years. But the formula was already there. Schwarzschild's solution revealed that such an object would warp both space and time to unimaginable extremes. As one approaches this heart of darkness, gravity grows so intense that escape becomes impossible, and time itself bends. Compared to a clock far away in the quiet depths of the universe, a clock near the event horizon ticks ever more slowly. The closer to the center, the more distorted the flow of time becomes. Black holes were only the beginning. As physicists explored Einstein's equations over the decades, stranger solutions emerged from the mathematics. Wormholes, warp-like geometries, even entire rotating universes, all of them born from the same insight. Space-time is not rigid. It is malleable. In 1919, observations during a solar eclipse confirmed one of Einstein's boldest predictions. Starlight passing near the sun was deflected by its gravity. The curvature of space-time had been seen. Einstein became an international icon overnight, but confirmation demanded precision. In 1971, Joseph Hoffel and Richard Keating conducted one of the most elegant tests of relativity ever attempted. They synchronized a set of ultra-precise cesium atomic clocks. Some remained on Earth. Others were flown eastward and westward aboard commercial jets circling the globe. The experiment cost thousands of dollars in airfare and required careful planning. But its implications were immense. The airborne clocks were not only moving relative to those on the ground, they also occupied slightly weaker gravitational fields at cruising altitude. After 2 trips around the world, the clocks were reunited. If Newton were right, they would still agree. They didn't. The differences were tiny, hundreds of nanoseconds, but decisive. Motion and gravity had changed the flow of time. And the most dramatic confirmation of general relativity came from something even subtler. Einstein's equations implied that space-time could ripple. Accelerating masses should send out gravitational waves, tremors in reality itself, though even Einstein sometimes doubted they were real. In 1974, Russell Hulse and Joseph Taylor found a pulsar, PSRB 1913 plus 16, orbiting another neutron star. Its steady pulses acted like a perfect clock. The orbit was slowly shrinking, as if energy were leaking away. The decay matched exactly what gravitational waves would carry off, earning them the Nobel Prize in 1993. Then in 2015, LIGO detected those ripples directly. 2 black holes merging more than 1 billion light years away. Space-time rang like a bell, and a new kind of astronomy began. Black hole mergers, neutron-star collisions, and perhaps one day, echoes from the universe's first moments. Einstein's equations also hinted at another shock. The universe is not static. Friedman found expanding solutions in 1922. Hubble confirmed them. Galaxies recede not like shrapnel flying through space, but because space itself expands. The Big Bang, 13.8 billion years ago, was the beginning of space-time. Yesterday there was less space. Tomorrow there will be more. The expansion rate is about 70 kilometers per second per megaparsec. Far enough away, galaxies recede faster than light, without breaking relativity, because the limit applies to motion through space, not the stretching of space between us. But expansion raises a quiet paradox. Photons get stretched as they travel, losing energy. Galaxies lose kinetic energy as well. Where does it go? Noether showed energy conservation comes from time symmetry. But an evolving space-time breaks that symmetry, so global energy conservation no longer holds in the usual way. Then comes Weinberg's sharper question: how can empty space expand? How can nothing grow? The answer is that space-time isn't a material substance. Expansion is a geometric change, not a physical medium stretching like rubber, which brings us back to time. In relativity, time is no longer universal. Each observer carries their own clock, shaped by motion and gravity. Near a black hole, time slows. Far away, it races. Our distant civilization exploited this, warping routes, lingering near deep gravity, watching the outside universe age. And as Einstein famously suggested, past, present, and future may be only a stubborn illusion. General relativity makes the universe feel less like a river and more like a finished landscape, one where every event already exists. But that leaves a final dilemma. If space-time is whole, if past and future are equally real, what becomes of change? Of becoming? Of the feeling that time passes? Relativity answers with a haunting picture. World lines. Every particle traces a path through space-time. Your body is a temporary convergence of countless world lines. Threads that gather, hold together briefly as you, then disperse again. You are not a point moving through time, but a structure written into it. So where is the problem? Without absolute time, there is no single cosmic now. And without a universal present, the equations seem to imply something staggering. The entire history of everything, past, present, future, is already there, inscribed in space-time. This is the block universe. It troubles us because it makes the universe feel less like a story unfolding and more like a script already written. We may still feel the past is fixed and the future is open. But are we mistaking experience for the deeper rules underneath? Consider something small and clean. Two electrons rushing toward one another, identical charges, identical repulsion. As they draw closer, the electromagnetic force strengthens. Their motion slows, stops, reverses. They fly apart, or receding back the way they came. Now film that interaction. Show it to a room full of physicists. First, flip the film left to right, as though reflected in a mirror. The audience will not blink. The laws still make sense. Physics doesn't care about left and right. Now do something more drastic. Reverse the film in time. The electrons now appear to come together, slow, stop, and move apart again. Perfectly plausible. The room still nods. Electromagnetism has no obvious preference for the direction of time. Neither does gravity. Neither does the strong nuclear force. The weak nuclear force is slightly biased, an almost whisper-small asymmetry. But for most of the universe's machinery, the fundamental interactions are nearly indifferent. At the microscopic level, time can run forward or backward, and the equations barely notice. And that leaves us with a profound disconnect. The large-scale world we live in clearly knows about time. Coffee cools, wood burns, supernovae explode. None of these processes naturally run backward. You cannot unscramble an egg. You do not watch smoke gather itself from the air and return to the match. But this seems almost paradoxical because our macroscopic world is nothing more than an ocean of atoms, and those atoms interact primarily through electromagnetism. An interaction that, as we just saw, does not care which way time points. So how can a one-way arrow of time emerge from countless microscopic interactions that are almost time-symmetric? How does time's direction appear inside a block universe? And there is another problem. The simplest block universe is infinite in both directions, stretching endlessly into the past and endlessly into the future. But our universe does not look like that. Observations tell us it had a beginning. Roughly 13.8 billion years ago, the universe was born, along with space and time themselves. We do not yet know what that birth truly was, or what, if anything, came before it. But from that moment onward, space-time was part of the universe's fabric. And the early universe was peculiar in a way that may be the key to everything. It seems to have been astonishingly smooth, hot, dense, and remarkably uniform. At first, smooth might sound like high entropy, like air spread evenly through a room. But gravity changes the story. For a universe dominated by gravity, smoothness is special. A smooth distribution of matter is not the most disordered state. It is a poised, low entropy beginning, because gravity has not yet done what it loves to do: gather matter into clumps, deepen wells, create structure. As the universe expands, gravity amplifies tiny imperfections. Matter collapses into stars and galaxies. Gravitational potential energy is processed into light, heat, chemistry, life, and then into waste. Entropy rises. The universe moves from that extraordinarily low entropy beginning toward a higher entropy future. And in that shift, from low entropy to high, time's arrow is stamped into reality. Roger Penrose, reflecting on the improbability of such a low entropy beginning, had estimated the odds of it arising by chance as roughly 1 part in 10 to the power of 10 to the power of 123. An absurdly tiny number, so small it hardly fits inside the mind. Something about our universe's birth was profoundly special, and this raises a haunting thought. Perhaps the block universe contains no built-in arrow of time at all. Perhaps the distinction between past and future, the very structure of our experience, depends on the Big Bang's extraordinary initial conditions. Without that beginning, would past and future mean anything? Could minds like ours even form a coherent picture of reality? It is difficult to imagine a universe without an arrow. But perhaps even our ability to imagine is, in some deep way, a consequence of that peculiar birth. And then, just when time seems like a story written into entropy, general relativity offers another, more unsettling possibility. On June 10, 1944, a British Halifax bomber was shot down over France during the D-Day campaign. All 7 crew members died. The pilot was a 33-year-old Dutch volunteer, Willem Jacob van Stockum. His name is little known today. Yet Van Stockum was among the first to uncover a mathematical doorway to time travel. In Newton's universe, time travel was fantasy. But in Einstein's, space-time could bend, twist, and in certain solutions, loop back on itself. General relativity was notoriously hard to solve, yet after Schwarzschild's black hole solution, physicists began exploring stranger geometries, expanding universes, curved spaces, and even rotating cosmoses. Building on earlier rotating models, A.F. Van Stockum examined what would happen to world lines in a spinning universe. He found something astonishing. Under certain conditions, they could close. A particle moving forward in time could return to its own past. These paths, closed time-like curves, were, in plain language, time travel. Though such universes may not describe our own, the implication was profound. If Einstein's equations permit time loops anywhere, might other extreme conditions allow them too? Van Stockum hoped to work with Einstein at Princeton. Instead, war intervened. He returned to Europe to fight, and his world line ended in a field in France. In 1949, Kurt Gödel rediscovered and deepened the idea. Having escaped war-torn Europe, Gödel befriended Einstein at Princeton and, for Einstein's 70th birthday, and presented him with a rotating universe solution containing closed time-like curves. Gödel's universe did not merely challenge logic, it challenged time itself. Like Van Stockum, Gödel had found the mathematics of a rotating universe, but his version was more refined, more philosophical, and more disturbing. In Gödel's universe, space-time itself rotates in such a way that closed time-like curves thread through the cosmos. World lines loop back. The future can intersect the past. When Einstein received Gödel's result, he admitted to being deeply unsettled. The theory he had created appeared to permit journeys into one's own past. Einstein had overthrown absolute time, only to discover that time itself might fold. Gödel later asked astronomers whether there was any evidence that our universe rotates globally. The answer, consistently, was no. His rotating cosmos does not describe the one we inhabit, and yet the door had been opened. If Einstein's equations allowed time travel in one possible universe, could other exotic geometries exist in ours? Physicists returned to the equations. Searching for further distortions of space-time, they found many. Add rotation to a black hole, a Kerr black hole, and space-time is dragged around with it, twisted into a vortex. In the mathematical ideal, passing through its interior might lead not merely elsewhere in space, but elsewhere in time. Or consider wormholes, bridges connecting distant regions of space-time. Under certain theoretical conditions, they could link not only two places, but two different moments. Whether such structures can physically exist is unknown. If perhaps the energy required to stabilize them exceeds anything the universe can provide, perhaps quantum effects forbid their formation, but within general relativity, the possibility remains. We now understand how Einstein's space-time behaves, how it bends, ripples, expands, and possibly loops. But we still do not know what it is. Where do we turn next? At the beginning of the 20th century, Einstein was not alone in reshaping physics. Quantum mechanics was rising at the same time, a revolution just as radical, but aimed at the smallest scales. If gravity governs the grand architecture of the cosmos, quantum theory governs its microscopic machinery. Perhaps physicists began to suspect the ultimate nature of space and time lies not in the vastness of galaxies, but in the trembling of the smallest possible scales. And so we return, all once more, to our distant civilization. The stars have long since died. Matter itself begins to decay. The cosmos approaches its final stillness. Their black hole sanctuary, once a source of power and stretched time, is no longer eternal. The great books had warned them, even black holes evaporate. But while general relativity binds a black hole together with overwhelming gravity, the quantum world whispers at its edges. Over unimaginable spans of time, quantum effects allow black holes to radiate, slowly losing mass, slowly fading. Hawking radiation ensures that even the darkest objects are not forever. For billions upon billions of years, physicists struggled to reconcile these two worlds, the smooth curvature of space-time and the jittering uncertainty of quantum mechanics. They fit together poorly. The language of gravity seems alien to the language of quanta. Even today, a student attending a lecture on general relativity in the morning and quantum mechanics in the afternoon might be forgiven for thinking the professors have ignored one another for a century. The equations do not comfortably merge, and yet, somewhere in that uneasy overlap may lie the final truth about space and time. In Rose Lawn Cemetery in Florida lies Paul Dirac, who died in 1984 at 82. He also has a memorial stone in Westminster Abbey near Isaac Newton. Like Newton, Dirac reshaped reality, but not by curving space-time. He revealed that even the quantum vacuum hums with hidden possibility, that his stone bears little more than his name and an equation, a compact string of symbols representing the first true union of Einstein's relativity and quantum mechanics. Born in Bristol, Dirac arrived at Cambridge in 1923, quiet, intensely focused, almost silent. Colleagues joked he spoke in Diracs, one word per hour. But while he spoke slowly, his mind moved fast. Physics was in turmoil. Relativity had transformed space and time, and quantum mechanics had shattered classical certainty. Yet quantum theory still rested on an outdated Newtonian stage. Dirac sensed the mismatch. If relativity was right, quantum mechanics had to obey it too. In 1927, after months of solitary thought, he found the equation he sought, a relativistic description of the electron. Suddenly, the electron's mysterious spin and magnetic behavior fell naturally out of the mathematics. But the equation contained a surprise. It allowed two solutions. One described the familiar negatively charged electron. The other implied a particle of identical mass but positive charge. Not the proton, something entirely new. Dirac had predicted antimatter. Soon after, the positron was discovered, confirming his theory. From this breakthrough grew quantum field theory and, eventually, the Standard Model. For every particle, a partner, electrons and positrons, quarks and antiquarks, mirror images emerging inevitably from the marriage of relativity and the quantum world. But there was a catch. Quantum field theory was built on special relativity, the flat, uncurved space-time of Minkowski. It assumes a stable stage, a universal arena in which fields can rise and fall, and in which time and space, though relative, remain smooth and background-like. General relativity refuses that. In Einstein's deeper theory, space-time is not a passive stage. It is dynamic. It evolves. It participates. It bends under mass, ripples with motion, stretches with cosmic expansion. And when we try to place quantum fields on that living, shifting geometry, when we try to quantize gravity itself, the mathematics explodes. Infinities appear, stubborn and uncontrolled, as though the theories are speaking incompatible dialects of the same language. So some physicists stepped back and searched elsewhere, not for a clever patch, but for a new foundation, a new idea of what space and time might be, or in hope of finding what is often called a theory of everything, a single framework that unites the quantum micro world with the gravitational macro world and explains the universe as a whole. But these candidate theories do not necessarily simplify the picture. In string theory, sometimes extended into M theory, reality may require extra dimensions, 11 or even 26, depending on the formulation. In this view, not only matter and forces, but space and time themselves emerge from the geometry of higher dimensional structures. Yet even here, a haunting question remains. What are these fundamental structures made of? The theory describes their behavior, their shapes, their symmetries, but the deeper substance remains elusive. Another contender, loop quantum gravity, is stranger still. It suggests that space-time is quantized, that at the smallest scales it is not continuous at all. Instead, it resembles an immense network, a dense weave of discrete links. To creatures like us, vastly larger than those scales, the weave appears smooth, just as a beach looks continuous from afar, though it is built from grains of sand. But again we can ask, what are those grains? What are the links in the network made of? And again, the answer slips away. Which brings us, in a sense, back to the beginning, back to Newton and Leibniz. Newton believed space and time were real entities, existing independently of matter. Leibniz argued the opposite. Space and time are not things, but relationships. Without objects to relate, space and time have no meaning. Einstein seems oddly to lean closer to Leibniz than to Newton. Matter shapes space-time, and space-time tells matter how to move. Reality is relational, intertwined. So what if we take that final step? What if space and time do not exist at all, not fundamentally? What if they are emergent phenomena, concepts that only appear at the scale of macroscopic beings like us? It sounds absurd, until you remember how often the universe works this way. We do not feel the expansion of the cosmos, even though it governs the largest scales. And we do not feel individual atoms striking our skin. We feel temperature, a bulk property that emerges from countless invisible collisions. Perhaps space and time are like that. Perhaps they are not the underlying truth, but the large-scale story that the underlying truth produces. In 1997, Juan Maldacena discovered a profound relationship between certain theories of gravity and certain quantum field theories, an idea now known as the ADS/CFT correspondence. It could be a mathematical coincidence, or it could be a clue, a path toward uniting quantum mechanics and gravity. And if this is the right path, something remarkable seems to follow. Space-time begins to look less fundamental, more like a pattern arising from deeper quantum relationships, as though the universe has a smallest possible resolution, a Planck scale graininess, a kind of cosmic pixel size. If so, then at the deepest level, there may be no space between the building blocks of reality, no time between one event and the next. Those concepts may simply fail, like trying to describe a color to a creature without eyes. Perhaps all that exists at the base are relationships, interactions, connections, rules, and if that makes you uneasy, you can place yourself inside the idea this way. We have already accepted that we are made of atoms. Yet, consciousness, this private, luminous sense of being, somehow emerges anyway. We live comfortably inside that mystery. Perhaps we must learn to do the same with the stage on which we exist. Perhaps space and time are part of the illusion that becomes unavoidable at our scale. And so we reach the end of our journey. Space and time began as the most ordinary of things, so natural we rarely notice them at all. Yet the closer we look, the stranger they became. Newton's simple absolute stage gave way to Einstein's flexible space-time. Quantum theory hinted that even space-time might have texture, might come in pieces, might be woven or pixelated, or might not exist as a fundamental entity at all. Have we moved closer to the truth? Maybe. Or maybe each answer only reveals a deeper question. The hope, still, is that a future theory, whatever form it takes, will finally illuminate the cosmic stage and tell us what space and time truly are. Perhaps the blocked universe will dissolve into something more subtle. Perhaps the present is built moment by moment by quantum processes. Perhaps some mechanism we cannot yet imagine defines reality in a way our minds are not yet shaped to grasp. But nature is not required to reveal her secrets. No matter how hard we work, some mysteries may remain mysteries. It is possible that the true essence of space and time will always lie just beyond our reach. And at last, as we return to the twilight of the universe, back inside that shell wrapped around a dying black hole, the last survivors watch as their ancient guardian slowly evaporates. They want only one more day, one more moment, anything that can be stretched from the thinning fabric of existence. They have manipulated space. They have mastered time, but they cannot defeat them. And then finally, the darkness arrives. If you're still awake, you can continue to the next chapter. Otherwise, I hope you sleep deeply and dream gently. Good night.